Okay, so let me go over some optimization and differentials. And since some of these questions are a little bit heavy, I think I can't do all the questions, but if there is any specific questions you're interested in, let me know. Okay, so I just chose 3, 4, and 5, and unless you have other specific questions. So in optimization, the most important thing is, one, you have to think of how the figure looks like. Usually when you have the figure, life becomes easier. So one, you have to sketch, then you have to find the formula or the expression related to the problem. So usually you're asked to maximize or minimize. So you take the derivative of that function, find the critical points, and then take the second derivative. And after taking the second derivative, you check whether whatever you're getting is a maximum or a minimum. Maybe as a reminder, recall that if I have a number C and I take the second derivative and I evaluate it at C, if this answer is a negative, then it means that C is a local maximum. In the same way, if I have a number C and when I evaluate the second derivative at that point I get a positive, then C is a local minimum. Okay. So in question 3, we have a rectangular garden which is 800 square feet in area. So they are telling us that my area is the same as 800 square feet. And this garden is to be fenced off against rats. Find the dimensions that will require the least amount of fencing if one side of the garden is already protected by a barn. So what they are saying is that we have a rectangular garden. So maybe this one, and we want to fence around this garden. So when you hear fencing around, so we are going to be moving around this garden. So right away we think of a perimeter, but they are telling us that one side of this garden is already protected by a barn. So which means when I'm fencing, I don't need to fence that side right there. Okay. This is a rectangle, so this rectangle has, of course, length and width. So I can call this length, I can call this width, depending on what you're really comfortable with. Yeah, but I think maybe following your notes, we can keep using X and Y. So the length of this rectangle is X, and the width is Y. And of course, we shall have another width here, which is also Y. But this side is just the way it is, because so this side we shall not have the length there, because we don't need to fence that side. Okay, so we want to find the dimensions that require the least amount of fencing. So what we want is to get the least amount of fencing. So what is the minimum of moving around this rectangle? So basically they want the minimum of the perimeter. They are basically asking us to minimize the perimeter. Okay. So from this figure, from this rectangle, my perimeter which I can call P, is the same as, we know what perimeter is. It is just sum of all distances around the figure. So this should be x plus 2y. So this x plus y plus y. If it was a full rectangle, then it would be this plus this plus this, then plus whatever is there. Okay, so the perimeter is x plus 2y, but we are given the area of a rectangle. We know what the area is, the length times width. So area is length times width, and our length is x, our width is y, right? But we are given that this area is 800. So therefore, I can find y, and y will be 800 over x from this guy here. Okay, now I can get this value of y and put it in the perimeter so that I have a function of just one variable, and I'll have the perimeter as a function of x, which is x plus 2 times y, but y is 800 over x. So this is x plus 1600 over x. I can write it nicely if I want, and I say maybe this is the same as x squared plus 1600 then over x. Now, that is the function of the perimeter in terms of x, or in variable x, and that is the function I need to optimize. And in this case, since I'm looking at the least amount, this is the function I'm hoping to minimize. Now, choosing to write p as a function of x, it is just a choice. Someone could make x the subject here, and then you substitute the value of x back here, and therefore you will have a function of y. Okay, so we want to find the derivative of this function, and this derivative is by quotient rule, x then times 2x minus x squared plus 1600 then times 1 then over the denominator squared, which is x squared. When I simplify this, I have 2x squared minus x squared minus 1600, and the whole of it over x squared, and this is x squared minus 1600 over x squared. We need to find the critical points of this, so we want those points where p prime of x is equal to 0, and when I equate this guy to 0, this means x squared minus 1600 is equal to 0. And that means that x squared is equal to 1600, and this means that x is equal to plus or minus 40. Okay, now you have to remember that we are moving around the fence. We are moving around a rectangle, so the answer we are getting right now is a distance. So if it is a distance, we can't expect it to be a positive, and therefore I have to discard of the negative, and I can conclude that therefore x is equal to 40. If you don't want to use that explanation for removing the negative, for sure you'll find that when we check for the second derivative and check at these 2 points, then you find that one of these points won't give you what you're interested, which is a minimum, right? Okay, so the second derivative, so when I take the second derivative of this function, so I'm differentiating this guy again, quotient rule, x squared times 2x minus x squared minus 1600, then times 2x, then the whole of it over x to the power 4. So p double prime of x is the same as 2x cubed minus 2x cubed, I hope you can see that, then plus 3200x, and the whole of this over x to the power 4. This is the same as, yeah, so we have, if this is 2x cubed, 2x times x squared, that is 2x cubed, 2x times 1600, that is 3200x. So therefore, this guy will cancel, and I just have my second derivative as 3200x over x power 4. So whether 1x can cancel, and I have 3200 over x cubed. Now, this answer we have here, remember we need to check the second derivative. So if I check the second derivative at a point 40, this is 3200 over 40 cubed. And you can see that whichever answer we get here is a positive. And we said that if that answer is a positive, then this point 40 is a local minimum, right? So we are saying that x equal to 40 is, and like I said, if you decided to check negative 40, you can see that when I substitute a negative 40 here, I'll have the whole answer as a negative. And if it is a negative, that means a local maxima, and that contradicts what we are trying to look for, because we are looking for the least, so we are looking for the minimum. But what the question is asking for, it is asking for these dimensions. So after finding the dimension of the width of the length, which is x, then I can substitute the value of x right here. So therefore, y is equal to 800 over x. X is 40, and this is the same as 20. Okay, so the dimensions of this that we require the least amount of facing, the length as 40 and the width as 20. Okay. In question 4, same thing, almost the same thing. We have a rectangular playground, and it is fenced off and divided into two parts by a fence parallel to one side of the playground. So once again, this playground is rectangular, right? And they are saying we want to fence off this, and it is divided into two parts by a fence parallel to one side of the playground. So I can say maybe that fence is this guy here. Okay. Now, note that one could choose to, because they are not specifying, they are just saying parallel to one side. So I'm choosing this fence to be parallel to this side here. But one could choose the fence to be this. You should be ending up with the same thing. Okay. Okay, so what does this mean? It means that in this rectangle, if the length is x, of course, this other length will also be x. If the width is y, then this will be y. But since the fence is parallel to the side y, then the fence will also have a length y, right? They are saying that 240 feet of fencing is used. So basically what they are telling us is that the perimeter, when I move around this guy, I get 240, and we want to find the dimensions of the playground that will enclose the largest area. Okay, so we know that the area of this guy, so the formula for the area won't change. So the area is the same as length times width, so that is xy. Okay. We have the perimeter of this rectangle. The perimeter of this rectangle, like I said, it is moving through all the sides, so it will be this plus this plus this plus this plus this, okay? Because we are fencing, this guy is a fence, so we need to fence the middle there. So that is why when we are fencing, we move all through the whole rectangle. Okay, so P is the same as x plus x, which is 2x, then plus 3y, right? But we are given this P as 240, so 2x plus 3y is equal to 240. Once again, we have our area as axy. I can substitute for y if I want. So from here, I have which one is easier to substitute for? I can substitute maybe for x. Let me show you that it's not always substituting for y. So I can substitute for x, and from here 2x is equal to 240 minus 3y, and therefore my x is 240 minus 3y over 2. So my area is the same as y, right? Then x, which is 240 minus 3y, and the whole of it over 2. And I can open up this, and I say this is 240y minus 3y squared, then the whole of it over 2. As usual, this is a function of y, and we need to take this derivative with respect to y, and this is the same as 240 minus 6y, and then the whole of it over 2. I can simplify this to 120 minus 3y, and that is our derivative. Okay, now we want to find the critical points of this, so values of y where this derivative is 0, and this implies 120 minus 3y is equal to 0. So my y is equal to 40. Remember, we are looking for the dimensions that will enclose the largest. So we want to maximize this area. So if I take the second derivative with respect to y, so I want to differentiate this guy here. Clearly I end up with -3. And -3 it is always going to be equal to, less than a negative, and therefore this point y that I find here, when I substitute it there, I always get a negative, and we can say that this 40 is actually no longer just a local maximum, but rather an absolute maximum or a global maximum. Okay, so that is the value of y, and we can find the value of x so easily. So we have that 2x is equal to 240 minus 3y, which is 3 times 40, which is 120. So 2x is equal to 120, and therefore x is equal to, x is equal to 60. Okay. Maybe question 5. So in question 5, once again, you see that for each of the questions, knowing how reading the question and you're able to sketch the figure, life becomes a little easy. So get used to sketching this figure. Okay, in question 5, we want to find the largest possible area for the rectangle with the base on the axis. So the base is on the x-axis and the upper vertices are on the curve y is equal to 7 minus x squared. So and I guess this point here should be 7. So when x is 0, this point here should be 7. This point here is just 7. So this point here is 0, 7. If you're very careful. And these points here are actually, so I can actually put those points. Not important, but so this is 0, 7. And this point here and this point here, negative square root of 7, and then positive square root of 7, of course 0, something like that. But really what we are interested in, the area of a rectangle which looks like this, and like this. So it has the base on the x-axis, and then two of its vertices are touching this curve here. Remember this curve, the whole of this curve is y is equal to 7 minus x squared. Okay, so this side, one side of the x, that is x, the other side is also x, and of course the height is our y side. Okay, so as usual it remains, this is a rectangle, so the area is the same as the length times width, but check that the whole of this rectangle has a total length of x plus x, which is 2x, then times the width which is y. But from the equation given, the equation of the curve, we can substitute for y, and therefore my a is the same as 2x into y, which is 7 minus x squared. So a is equal to 14x minus 2x minus 2x cubed. Okay. This is a function of x, so when I take this derivative, I'll have 14 minus 6x squared. We want to determine the critical points, so we want to find those values of x where this derivative is 0. So this means that 14 minus 6x squared is equal to 0, and this means 6x squared is equal to 14 over 6 over 6. And we have x squared to be equal to, I can reduce this by 2, 3, by 2, 7. So this is 7 over 3. And this means x is actually plus or minus square root of 7 over 3. Once again, x is the length of a rectangle. So even before I check the second derivative, I know that this guy here should not be there because it's a length. So therefore, my x is just positive 7 over 3. Okay? And this time we want to find the largest possible area. Now we need to check that this guy gives a maximum, so we need to take the second derivative of this. And when I take the second derivative of this function here, then I get minus 12x. And you can see that when I evaluate this guy at root 7 over 3, then I'll have negative 12 times root 7 over 3. And this answer is always a positive. So therefore, this root 7 over 3 is actually, so therefore I'm saying because of this, then this guy here is in fact a global or an absolute minimum. Oh, sorry. This is less than 0. And therefore, this is an absolute maximum, right? Okay, so remember we need to find the largest possible area. We have this point root 7 over 3 as a maximum, and therefore if I get this root 7 over 3 and I substitute it back in the formula for the area, then I'm getting a maximum, right? Okay, so what I'm saying is that therefore the largest possible area is A evaluated at square root of 7 over 3. So I'm getting square root of 7 over 3 and I'm substituting it here. Note that you could, if you wanted, you could use this x to find y, and after finding y, you just substitute here. That is the same thing. Okay, so this is 2x, so this is 2 times square root of 7 over 3, then into 7 minus x squared. When I square this guy, I'll just have 7 over 3. So this is 2 times square root of 7 over 3 into this is 21 minus 7 over 3. Okay. And this is 2 times square root of 7 over 3 times 21 minus 7, that is 14 over 3. This 14 can multiply with 2 to give me 28, right? Then over 3. So I'm getting 14 over 3 times 2, which is 28 over 3. Then times square root of 7 over 3. You can stop here if you want, but if you want to do more, especially the answers of the multiple choice questions, what we want to do is just rationalize this. So root 7 over root 3, and when I rationalize here, I'll have root 3 over root 3. So I just have 28 over 3 times root 7 times root 3, then over root 3 times root 3, which is just a 3, right? And finally, I have 28 root 7 times root 3, that is root 21, then the whole of it over 9. Okay. Is that fine? Okay, that is good. So Okay, so 14, 10, 9, and 6. So this is 5. So I'll first do 6 maybe. So 14, 9, and 14, 10, 9, and 6. Okay, so let's start with question 6. Question 6 is right here. Okay, so in question 6, we want to find the coordinates of the points on the curve this that are closest to the origin. Once again, we should be able to sketch this curve. So one thing we know is this one looks like this curve up here. The only difference is that we have some coefficient here behind y. So this doesn't change the shape of the curve, it just changes where it cuts the axis really. Okay. So this curve is the same thing, and this curve is the same as something like that. And you can see that when x is 0, y is 28 over 4. So this point here is a point 28 over 4, which is like 7. So this point here is 0, 7. And when y is 0, this point here, these points here, this is negative square root of 28. This is positive square root of 28. But really, that's not important. What is important is that they are telling us that we want this curve and we want to find the coordinates of the points. So we want to find this point here, which I can call x, y. So we want to find the values of x and y, which is closest to the origin. So which is closest to the origin, to the point 0, 0. Okay. Now, we all remember the formula for the distance of a line. If we have a line between 2 points, maybe I can just remind us. So if we have 2 points, x1, y1, x2, y2, then the distance between these 2 points is the same as I can say x2 minus x1 squared plus y2 minus y1 squared. Now, under a square root, so if I square both sides, you see that the square root will go, but I'll have a square right here. So that's what I want. Okay. So what the question is asking for really is what are the values of x and y such that the distance from that point to the origin is the shortest, is the shortest distance. That's all we are interested in determining. Okay, so I can write the same formula. So in this case, our x1, y1 is 0, 0, x2, y2 is just xy. So I have the distance squared is equal to x2, so which is x minus 0 squared plus y minus 0, then squared. And this is the same as x squared plus y squared. Okay, but I know what y is. I have y from this from the equation of the curve. So we have d squared is equal to x squared plus y squared, and y squared is the same as 28 minus x squared, then over 4 and the whole of it squared. Now, you might be tempted to take the derivative here, but this is just an expression of x, which is denoted as d squared. So this expression of x, but you can just say that, hey, the whole of this expression, because this is the expression of the distance, okay, so I can just say, let this expression be denoted by maybe capital D. So I have that 10 plus 28 minus x squared over 4, and then the whole of it squared. So now I have a function, and I'm interested in the closest or the shortest distance. So I'm interested in minimizing this guy here, okay? So once again, this is a function of x, so I can differentiate it with respect to x. And when I take this derivative with respect to x, maybe let's first simplify this further. So this is x squared plus 28 minus x squared squared, then over 4 squared, which is 16. And I can write this as 16 x squared plus 28 minus x squared squared, and then the whole of it over 16. So I'm trying to take the derivative of this, and this derivative is the same as 32x. So this is 32x. Then plus, when I take the derivative of this guy here using chain rule, that is 2 times 28 minus x squared, then times the derivative of the guy inside, which is negative 2x, and the whole of this guy is over 16. Okay. I want to find the critical points. So the critical points are when this derivative is 0. So this means that this is 32x minus, this is 2x times 2, that is 4x. 4x times 28, that is 112. So minus 112x, then plus negative times negative, that is a plus 4x cubed. Negative 2 times 2, then times x squared times x. Okay. So this guy is equal to 0, because when I equate this to 0, the 16 will go away. That is why I'm just writing this guy here. So this means 4x cubed, 32 minus 112, that is the same as minus 80x, and this is 0. So I can pull out 4x, and this will be x squared minus 20, and this is equal to 0. And what does this mean? This means that either x is 0 or x squared minus 20 is 0. So x squared is equal to 20, and x is plus or minus square root of 20. For the same reason, we are trying to find a distance. So it cannot be a negative, right? Now, this distance we are trying, if you say that it is 0, then you're being too obvious, because I mean, if you say that distance is 0, then you're not leaving the origin. So therefore, this one here is also out, and we just have x as square root of 20. And they are interested in the coordinates, and once again, you can take the second derivative of this guy to check that this is a minimum. So we want to take the derivative of this, the second derivative of this guy. And when I take this second derivative, what do I want to differentiate? I want to let me first simplify this further. Maybe 32x minus 4x into 28 minus x squared, then over 16. I can differentiate that the way it is, so that is 32. Now I can differentiate, maybe we should open up this to make life easier. So this is 32x minus 112x, then plus 4x cubed. Yeah, so we have that guy already. We have it here. So this guy, I just have to divide it by 16. So when I take the derivative of this, the second derivative, that is 32, then minus 128, which is negative 80, right? So this guy will be negative 80. In other words, I'll have something like 12x squared. Okay, I'm differentiating this guy here, 4x cubed, then minus 80. I'm differentiating 80x. And this guy here, of course, it is the whole of it is over 16. You can reduce this if you want. I can see that I can divide by 4. So I have 3x squared minus 20, then the whole of it over 4. Now, if you substitute this square root of 20 here, square root of 20 squared, that is just 20. 20 times 3, that is 60. 60 minus that is 40. And 40 over 4, we have a 10. And this is a positive. So the second derivative evaluated at this point here, we get a positive answer. So what I'm saying is that therefore, this guy at evaluated at square root of 20, I think we got a 40, and this is a positive, and therefore we are saying that therefore this point here is a minimum. And you see, that is why we are interested in the coordinates that minimize that distance, because we are interested in being closest to the origin. So our x value, our x coordinate is square root of 20, and when I have my x coordinate as square root of 20, I can just find the y coordinate from the equation. So we have 4y. So I have 4y is equal to 28 minus x squared. So 4y is equal to 28 minus root 20 squared, that is 20. So 4y is equal to 8, and therefore y is equal to 8 over 4, which is just 2. That is question 6. I hope that is okay. Then D said that question 9 and question 9 is the same. So 6, 7, 8, and then 9. Okay, so we have question 9, and question 9 says that let we have a closed top box. So a closed top box with a square base is being constructed with two different types of material. The material for the lateral faces, so this is a box. So first of all, this is a box. Let me try to draw it nicely. Okay. So roughly this is my box. So when they say that the lateral faces, so the lateral faces, they mean the side. So this guy here, this guy here, then this guy here, and this guy behind, this guy behind here. So those are our lateral faces. So we have a certain material um, for the lateral faces, and that material costs $6 per square inch. The material of the bases, so we have this base here, this base down, and if we flip this box, then we shall have that top as the base. So the material for the bases costs $2 per square inch. If the desired volume of the box is 50, find the length of the base edge that minimizes the total cost of the materials. Okay, so one thing is that we have the volume. Now you should remember the volume of a box, right? A box can be two types. It can be a tube or it can be a cuboid. Now, if they say that it has a square base, then that is a tube. If it has a rectangular base, then that's a cuboid. But generally, the volume of a box is the length times width, then times the height, right? Now, so length times width times the height. So if the base is a square, then the length and the width are the same, right? So basically, I'm saying that if the length is x, then the width will also be x, but we don't know, the height can be anything, right? So from our question, therefore, our volume is the same as 2, not 2, but x times x, which is x squared, then times h. And this means x squared times h is 50, and we have our h as 50 over x squared, right? Now, remember they are saying that the bases, so the top and the bottom, have a total area of what? So the base, the area of the base, because the base is a square, so the total area is length times width, which is just x squared. Of course, if this is x, then the the top also has the length as x, so these guys are also x. I hope you can see that. So this area of the base is x squared, and the area of the top is also x squared, and therefore the total area, so let me write that. So total area of the top plus the bottom is x squared plus x squared, which is the same as 2x squared. And 2x squared, this is area, so this is square inch, right? Now, the material for the top and the bottom is the material for the bases. It costs $2 per square inch. So if each square inch costs $2, how much would we pay for a total of 2x squared? So it means that the total cost for the top and bottom is $2 times the square inches that we have, and this is 4, and this is 4x squared. Same thing with the lateral faces. Now the total area for the lateral faces, so area of the lateral faces, so lateral is like this. You have to know, so once again, we have 1, this is the first one, 2, this is the second one, 3, this is the third one, then 4 side here, okay? So there are 4 lateral faces, but each face has an area of length times width, so x times h. I hope you can see that, x times h, x times h, and so on. So each of them has an area x times h, and there are 4 faces, so the total area is 4 then times x times h. Now, they are saying that the material for constructing each of the lateral faces costs $6 per square inch. So if we have 4xh square inches, then the total cost is the same as the $6 for each square inch, then times how many square inches we have. And this is 24x, and this is 24xh. Now, what we are interested in, we were interested in finding the edge, I mean the length of the base, so finding the value of x that minimizes the total cost. So what will be the total cost? Total cost is some function, let's call it c, and this function is the cost for constructing the bases plus the cost for constructing the lateral faces. So this is the same as 4x squared then plus 24xh. So therefore, this is 4x squared plus 24x. And my h, we know what h is. H is the same as 50 over x squared. So I can substitute 50 over x squared here. And we have something that is nice. So plus this x, so 1x here can reduce with this 1x, and we shall have 24 times 50. 24 times 50, I think that's 1,200, maybe. So 1,200 then over x. So this is our function we have, and this is some function of x. We are interested in minimizing this, so once again, we take the derivative of this function, which is 8x minus 1,200 over x squared by quotient rule, okay? This derivative equal to 0 means that 8x minus 1,200 over x squared is 0. What does this mean? This means that 8x cubed minus 1,200 is equal to 0. So 8x cubed is equal to 1,200, and x cubed is equal to 150. Okay, and therefore we have my x as the cube root of 150, and that is basically what they are asking for. and they want you to find the length, which is the value of x, and that is the value of x. Now, if you want, like I said, if you want, you can check that this guy here minimizes this function. And how? Once again, you take the second derivative of this guy and you substitute this value here. So maybe let's do that. So you take the second derivative of this function and we shall have 8. Is this a plus? Maybe plus, I think 1200 over x cubed. Let's check that real quick. So minus, so we want to differentiate this. This means minus, so 0, yeah, 2x squared. Oh, yeah, I guess this is 2400 probably. Okay. Check that we are taking the correct derivative there. So where you can see that this function is a positive. So when I substitute the cube root of 150 inside here, so when I evaluate this second derivative at cube root of 150, you see that I'll always have a positive answer, and therefore this point here is a minimum. Okay, I hope that is fine. So that is question 9. D, is that fine? Okay, let's see, you said question 10 and 14, so let me see what those say. Question 10. Okay, so in question 10 we have an open top box is made from a 3-inch piece. So an open top box is made from a 3-inch by 3-inch sheet of paper. So piece of sheet metal by cutting squares of side length x from each of the corners of and folding up the sides. Find the value of x that yields a box with the maximum volume. So so that we have it is made up of a sheet which is like this. In fact, let me not draw a rectangle, it's just a square. So I hope that looks like a square, and it is a 3 by 3, so it has 3 by 3 right there, right? Now what they are saying is that we are cutting length x at each of the corners. So we are cutting some small squares right here at each of the corners, and these squares are the same as they have the length x, right? Now you see that for each side for each side, since these are squares, then of course this side is also x, this is also x, this is also x, this is also x. Okay, so you see that if the whole length was 3, so if the total length of this guy here was 3, then this guy here that is left is 3 minus 2x. I hope you can see that. This is x plus x, that is 2x. Then I remove this from the whole thing and I remain with 3 minus 2x, right? I hope you can see that. Okay, so they are cut from each of the corners and folding up the sides. We want to find the value of x that yields a box. So we are interested in a box with a maximum volume, Now remember, once again, if I draw my box, say this is my box. So if this is my box, what is happening? Remember what we are changing. This guy here is the top, of the box. So you can say it is this guy here or this base here. Okay, but now its length, the length of the top or the base, you can see that since we've cut off these small square pieces, then we are left with a distance of 3 minus 2x, and therefore this guy here, this is 3 minus 2x, but this is a square base and this is minus 3 minus 2x, right? But this height, it remained the way it is. Okay, now we are interested in the volume, and we know what the volume should be, the volume of a tube, and this volume is the same as V, is the same as length times width times height, and this is x times 3 minus 2x, and then times 3 minus 2x. So my V, which is actually a function of x, is x times 3 minus 2x, and the whole of it squared. We are interested in finding x that minimizes this. So if I take the derivative by product rule, this is x, then times 2 into 3 minus 2x times negative 2. I hope you know how I got that. Then plus 3 minus 2x, the whole of it squared. Okay. If we try to simplify this, what happens? 2 to 4, so negative 4x into 3 minus 2x, then plus 3 minus 2x, the whole of it squared, and that is my derivative there. I can see that I have 3 minus 2x common, so if I pull it out, I have minus 4x plus 3 minus 2x. Is that fine? I hope that is fine. So this is 3 minus 2x, then into 3 minus 6x, and that is my derivative. Okay, now v prime of x equal to 0. This implies that 3 minus 2x is equal to 0. So this means 2x is equal to 3, and this means x is 3 over 2, or 3 minus 6x is equal to 0. So 6x is equal to 3, and therefore x is equal to 1/2, right? Now, this is a perfect example for what we've been talking about. We have two critical points, they are all positive, so we need to check which one of those gives a maximum volume. So we take the second derivative of this function once again. So I'm differentiating this function here, and when I take the derivative by product rule, it is 3 minus 2x times negative 6, then plus 3 minus 6x times negative 2. I hope that is fine. This is negative 6 into 3 minus 2x, then minus 2 into 3 minus 2x. Okay, when we substitute 3 over 2, let's check quick. If I substitute 3 over 2, wherever there is x, what happens? I get negative 6 into 3 minus 3 over 2, so that is just a 0, right? Then I'm left with minus 2 into 3 minus 3 over 2, that is also 0. So that one doesn't give us a conclusion, and therefore this guy is out. If I substitute 1/2 wherever there is x, I'll have negative 6 into 3 minus 2 into 3 minus, oh, sorry, I think we made a mistake. So this should be minus 2 into 3 minus 6x. Yeah, okay. So maybe once again, when we substitute 3 over 2 here, this is 0, right? Then we are left with minus 2 into 3 minus 6 times 3 over 2. So this is 3. That is also a 0. Yeah, we are right. So this guy doesn't give us a conclusion. When I substitute 1/2 right here, I'll have negative 6 into 3 minus 2 times 1/2 minus 2 into 3 minus 6 times 1/2. And what I have is minus 6 into 2 minus 2 into 0. So this is a 0. So you see we have minus 6 times 2, which is minus 12. So V prime prime at 3 over 2 is inconclusive. So we can't conclude. But when we have this guy here, this is the same as minus 12, and you see this is less than 0, and we said when the second derivative at a certain critical point is less than 0, then we have a maximum. So therefore we can conclude that our value of x that maximizes the volume is x equal to 1/2. Mm. You're asking how did you evaluate the height to be x? It is right here in the question D. So they are saying that by cutting square, so what we are given is the length of the sides of the bases, right? So we don't know the base, I mean the, so it's like when you just say, hey, maybe let it be h. So I'm just calling it a side x, because what you're interested in is to find is to find the is to find the volume in terms of x. Okay?
Um, hello.
Yes, please.
Um, how how do I say this? How are we sure like the height wasn't cut off? Like the edges of the height wasn't cut off?
Pardon that?
The edges of like the lateral sides of the cube.
Yeah.
How are we sure the edges weren't cut off, like the base?
Oh, how are we sure that the edges are not cut off?
Yes.
You mean like how are we sure that these edges are not cut off?
Yeah, and the height.
Because they just mention it here that an so an open top box is made from by cutting squares of the side of length from each of the corners and folding up the sides. Oh, how are we not sure that? So this is the thing. So since this is actually a cuboid, then you can because if I sit my box on this, then that becomes my base, right? If I sit it on this side, then it becomes my, so since it is a tube, then you can cut the sides, the squares of length x from any of those sides. I don't know whether that answers your question.
Okay, no problem. Thank you, sir.
Okay. Okay, then maybe finally, question 14. Um, so we have A and B as two positive real numbers, and we have that relation 4A plus 5B is equal to 7. Then the maximum product of A and B. So they are just telling us that maybe okay, so what they are interested in is the product, and the product, I don't know, you can give it any name. So which function should we give it? Maybe product P of A and B. That is what they are asking us for. So we want to maximize this product. So P, I can write this P as either function of A or a function of B. So if I write this as a function of A, this is A, then times B, but B from the given relation is 7 uh, minus 4A, then over 5. I hope I hope that is correct. So this is 7 minus 4A, then the whole of it over 5. Can can open up this, and this is 7a minus 4a squared, then over 5. When I take this derivative with respect to a, I'll have 7 minus 8a, then the whole of it over 5. This guy equal to 0 means 7 minus 8a is equal to 0, and 8a is equal to 7, and therefore my a is equal to 7 over 8. Yeah, that is really so. So then the maximum product of A and B is, so this is the critical point we have. We want to check that this critical point is a maximum, because we are interested in maximizing. So we can take the second derivative of this function, and the second derivative of this function, clearly it is negative 8 over 5, and this is always less than 0. And therefore, I can say that A equal to 7 over 8 is a maximum, a global, an absolute maximum, right? So the maximum product is the product that we get by evaluating this product at a point 7 over 8, and this product is the same as 7 over 8 into 7 minus 4 times 7 over 8, then the whole of it over 5. I'm substituting this value right here, okay? Maybe 7 over 8 into 7 minus by 4, 1 by 4, this is 2. So this is 7 over 2, then the whole of it over 5. Let's see what we get. Maybe 7 over 8 into 14 minus 7 over 2 times 5, which is 10. So this is 7 over 80, then times 7, and this is 49 over 80. 14 wasn't really so difficult. So, okay, is that fine, D? Okay. Um, does anyone have a question in quiz 28? So quiz 28 is just about differentials. Anyone wants a clarification in quiz 28? Okay, so maybe I'll just maybe do only one. So yeah, when we use differentials, what we want to do, we want to approximate a certain value, right? And so what you do is, if for example we are asked for the square root of a certain number, then this number doesn't have a perfect square root that we know. So we want a number that is closest to this number that you're given and can be evaluated so easily. So it can be a square root, can be a cube root, can be a natural log, it can be anything really. And the relation we use is we want to approximate a certain function, and it is approximated as f of a, then plus f prime of a into x minus a. Now, what I'm saying is that a is a value which is closest to the given value, but it can be evaluated so easily according to the given function. I hope that makes sense. So From this formula, you realize you need to have a function, you need to take its derivative, and you need to know what a is. Now, if I'm given a function, if I'm given a value like that, then my function is whatever is given, but instead of a number, it has x. So this is the square root of x, or x equal x to the power half. I need to find the derivative of that function. So I need to find the derivative of this, which is 1 half x to the negative 1 half. Now, I'm trying to evaluate a square root of 80.9. So I need to find a number that is closest to 80.9 and has a perfect square root. That number is 81. Now, check that one might say, hey, but 100 also has a perfect square root. Yes, 100 has a perfect square root, but we are looking for one that is closest to 80.9, okay? So after determining that, then we know our A, and our A is 81, whose square root is 9, right? And therefore, now I want to approximate this function, which is 80.9. And like we are saying, this is the approximately f of a, which is square root of a, which is square root of 81, plus f prime, which is 1 half, then evaluated at a, so 81 to the power negative 1 half, then into x, but my x is 80.9, then minus 81, okay? This is 9 plus 1 over 2 times 9. I'm bringing this guy down, then times 80.9 minus 81. This is minus 0.1, or we can say minus 1 over 10. So this is 9 plus 1 over 18, then times negative 1 over 10. So this is 9 minus 1 over 100, 180. Okay. And basically that is how, as long as you remember this formula, then you can always approximate all these functions. So approximately this value is 8.9994, something like that. And if you have if you're like practicing and you take the square root of 80.9 on your scientific calculator, you see that you get a value that is really, really very, very close to the value that you approximate. Okay. Okay, so that is what you'll be doing in quiz 28. Uh, okay. Any questions? Any particular questions? If not, I would love to not waste your time by doing the stuff you already know. Okay, thank you guys for joining. Today we were more, so thank you for joining, and I hope to see you on Tuesday.